Hey gang, and welcome to the Worksheet Solutions Walkthrough for the worksheet, Deducing Structures from NMR Spectra, Part 1. If you are here and you are feeling frustrated about NMR, proton NMR, don't worry gang. This was something that took me quite a while to get okay at. It just involves a lot of practice, and what I think is very important is it's easy to get overwhelmed. So if you're coming here for answers, don't worry, we're stepping through this worksheet. Obviously there's the walkthrough for part 2, but just hopefully this helps you reinforce the procedure or the process that I think might be helpful in solving NMR problems, or at the very least we're getting some more NMR reps. You're getting another explanation. Don't worry, you're getting the knowledge in your brain. You will get good at NMR. If you're feeling frustrated, that's my little pick-me-up speech to you. But enough talking, time to look at the worksheet. Okay gang, so the way I want to do these, it will take forever otherwise. I'm going to throw everything up here. I'm going to show the degrees of unsaturation calculated. I'm going to show the chart made. I will quickly explain this, dig into the chart to make sure you understand why everything is present. Then I'll show you how, given this information, we can actually get the structure. And then that's how all 4 of these will go in this walkthrough, as well as the other, part 2. Okay, so first thing we see, we are given the spectrum, and we have a molecular formula. So the first thing we're going to do is we're going to make sure we remember our degrees of unsaturation formula, which is 2 times the number of carbons plus a generic 2 that's built in, plus the number of nitrogens minus the number of halogens, I believe, and then minus the number of hydrogens, all divided by 2. I believe that's what it is. I'm sorry if that's wrong. I don't know if I have it memorized off the top of my head, but I'm pretty sure that is correct. Regardless, I know it's plugged in correctly up here. So if we plug this in, we see that our degrees of unsaturation, right, we have 12 minus 10 is 2. 2 divided by 2 is 1. So we have 1 degree of unsaturation. So we have either a double bond or we have a ring, okay? So the next thing is, that's step 1. Step 2, let's build our chart. So if we take a look up here, you can see I've labeled our peaks A, B, C, and D. You can order them whichever way you want. If you're following along with this video, it would be helpful for you to label them the same way. I just labeled them so when I have this chart, I have some label to give my rows so I can easily go from the spectrum to my chart and vice versa. Okay, so if we dig in to A, and so also be cognizant of the fact that my board is limited space. I did steps of 0.5 as far as chemical shift going here, and then up to 4, and then I have steps of 1 further downfield. Remember, using that terminology. This is more upfield, more downfield. This is when you're de-shielded. This is when you are shielded. Okay? So, looking here for A. Again, if you got slightly different numbers, right, that's just because I made this worksheet up. So, I really wanted to try and hit this peak a little bit above 2.5. So if you had something close to 2.6, 2.5, excellent, right? So this column is our chemical shift. So for A, 2.6 makes sense. We're gonna go peak by peak. We see that A looks like a triplet. Remember, 1, 2, 3. That's a triplet, right? You go by the peaks in the signal. So we see that the integration numbers are in red. Here, A has an integration number of 2, so it's 2. So because A is a triplet, remember, we determine splitting patterns using the n+1 rule. So what I like to do, I like to have this column called neighbors, because it makes you think how many hydrogens are actually surrounding this location, that this peak is corresponding to. And that means 2 neighbors. So here we don't see a lot of neighbors. So because we're 2.6 chemical shift, we are the most downfield out of all of these peaks. You know what? We'll do this part last. We'll do the appearance column last. Actually, we'll do it right now. So because we're so downfield, but not crazy downfield, right? You're gonna grab your chemical shift table, right? Whether the one from your class or the one I've linked for you. And you're gonna think to yourself, okay, so we only have 2 neighbors and we're pretty downfield. So in my mind, what that makes me think is one side of us, there are no neighbors, okay? However, we have neighbors on one side. So in my head, if you look at your chemical shift table, you're gonna see that being alpha to a carbonyl, alpha meaning right here, this is the alpha position, like lowercase Greek alpha, or the fish symbol, I can't draw it correctly. There we go. That's when you're just next door to a carbonyl. There are no hydrogens on a carbonyl carbon, meaning you have no neighbors. So if you want to think about it, if we had a carbon chain, right, this is a situation where, okay, I have 2 hydrogens here, which would be my integration of 2, but I have neighbors here, but no neighbors here. And because there's this electronegative oxygen right here, it's sucking electron density, not just out of this carbon, but even this carbon next door, this would de-shield that carbon, make its signal appear more downfield. So that's why initially, this column can be wrong. It's kind of your initial hunch. I think being alpha to a carbonyl makes sense. You're not going to be in the end of the chain, because if you're on the end of the chain, you wouldn't have neighbors, but you're going to be on the other side of the carbonyl that's embedded inside the chain. So that's why I said downfield, a few neighboring H's. Looks like we're in the middle of a chain, possibly, with a carbonyl, which would be good because that might explain our degree of unsaturation. Okay? So B. Let's take a look at B. So we're going from downfield back upfield. So B is downfield as well. Chemical shift over 2. I probably drew it not so great, but I was aiming for something 2.2 in the low 2s. It is a singlet, okay? So, and has an integration of 3, right? We see the 1 peak, so it's a singlet. So n+1 rule means we don't have neighbors, right? These hydrogens aren't splitting with any other hydrogens. So if we are downfield, a singlet, splitting with no one, this is a very common, so if you look at your chemical shift table, this is classic being alpha to a carbonyl, but being terminal. Because, like I was just drawing up here, when you have a situation like this, you are the end of the chain. You are not splitting with anybody, but you have the de-shielding effect from this carbonyl oxygen sucking electron density out of both of these, this carbon more so, but this also happens as well. So this is looking pretty good, at least in terms of the appearances we've listed, as well as the degree of unsaturation we may have already discovered. So letter C, we see we have 1, 2, 3, 4, 5, 6, a sextet. That's 6 peaks. I can't use my fingers. We are roughly in the neighborhood of 1.5, so 1.6, 1.5 is a good answer for the chemical shift. Sextet, right? 6 peaks. Our integration is 2, as seen in red. So if we're a sextet, n+1, right? Take that 1 away, n is 5. We have 5 neighboring hydrogens that this position is splitting with. So we have 2 hydrogens, which is also what I like to do, is I really draw this part first. I draw the hydrogens I'm dealing with. Now, we're a little downfield in terms of just seeing like regular old, hydrogens off of a carbon. Little downfield, so maybe we are semi-close to that carbonyl carbon, but farther away. But we have quite a bit of neighbors. So if you think about it, we have 5 neighbors, so maybe we have 2 on one side and 3 on the other. And then down here, last but not least, I hope, this is problem 1, but when you see something like this, when you're floating around 1, either just above 1 or just below 1 or on 1, and you are a triplet, that is so classic of being a terminal CH3, okay? So roughly 1 on the chemical shift, we have a triplet. The integration is 3. Because it's a triplet, right, n+1, take the 1 away, we're down to 2, right? So we have 2 neighbors. So I hope that you can see that this would be really good if we have a terminal CH3. There's no electronegative atom even close to this thing that's going to make its signal appear more downfield. It's just a straightforward CH3 on the end of our chain. Okay, so what I like to do, I think B is our biggest clue. So if we did something like this, and let me draw the hydrogens, and let me label this, what this corresponds to peak-wise. This would be letter B. I think this is pretty good. So we are downfield because of the carbonyl. We are a singlet because there are no neighboring hydrogens to split with. I think that's good. So we've now knocked out the degree of unsaturation as well as one whole signal. So I'm going to put a check mark here. Okay? So then let me just draw another carbon. And let me just assume that my chain is going to go on. Let me just kind of cut it right here. Let me see if I can explain this. So this would maybe correspond to peak A, right? 2 hydrogens here. So no neighboring hydrogens next door, but this would cause it to be downfield, right? So to make this work, right, everything's looking good because there's 2 hydrogens corresponds with our integration number. I can just keep drawing my chain. So let me, at this point, right, we've had 1, 2, 3, 4. Let me just finish this off. So now, if we take a look at this structure, 1, 2, 3, 4, 5. Let's make sure that this might fit our needs. So I have 2 hydrogens here. I have 3 here. So the chemical shift and everything checks out here. Let's make sure the splitting pattern did. So we have 2 neighbors. So this would come up as a triplet, right? Because 2 neighbors plus 1 would be 3. That is exactly what A is. I think this is a good representation of A. So I'm going to tackle this terminal case real quick. Super upfield, nothing would make it appear downfield, right? We have the triplet, 2 neighbors. This looks good. This would be letter D. And does C check out? Does C check out? So a little downfield, right? We are not too far. We would not be too far away from this carbonyl carbon. Good. That's the 1.6. Makes sense. So do we end up being a sextet? We do have 5 neighbors, right? 3 and 2. So then that would make it, 5 plus 1. This is C. So I hope that, I think the biggest clues were your ends, right? This was an end. This was an end. So this helped us determine, this and this. This helped us determine it was a carbonyl. That was our degree of unsaturation. We had an end here. We really just needed to connect the 2 and then see if they fit in between, okay? All right, on to problem 2. Okay, gang, on to problem 2. And I'm gonna try and do this a little bit more efficiently than the first one because I got a little bit too in the weeds. So, if we take a look here, look at your formula. Step 1 is calculate those degrees of unsaturation. So here, you can see that we ended up with 2. So remember, degrees of unsaturation. Rings, double bonds. So, in taking a look at our spectrum and completing step 2, which is populate our chart, I think it's very easy to rule out rings being part of our degrees of unsaturation because of 2 signals in particular. That would be both B, sorry, not B. It would be both A and D. Sorry. Oh my goodness. I'm so sorry. It is both A and C because they end up having no neighbors. They're singlets, right? If you think about a ring, there would be more symmetry if we had a ring and some other degrees of unsaturation. So I think it's safe to say that we have a couple of double bonds here. And if you went through you went through and you made the chart just to pick out some key characteristics, right? We see this singlet here has a shift of 3.5, right? So a chemical shift of 3.5. So no neighbors, and it's more downfield. So more downfield than a typical being alpha to a carbonyl. So maybe it's in between, wedged in between carbonyls, right? That would ensure no neighbors, and that would de-shield it further and put it farther downfield than that typical low 2-ish type chemical shift, okay? And then if we look at B, right, we do see that low 2, above 2, but below 2.5 chemical shift. We have some neighbors, but not too many, okay? So maybe on one side there's a carbonyl, maybe on the other side there's the extension of our carbon chain. And if you see in C, right, we have that classic low 2 chemical shift. We're a singlet. So this really looks like the end of a carbon chain, alpha to a carbonyl, right? That's what the appearance looks like there. And I hope if you saw D, it's Old Faithful. It's that terminal methyl group, right? The terminal CH3. So in taking this information and drawing a structure, I think the ends, we can at least with A and D, put something together like this. So this, I believe, explains C. This explains C. I'm getting all mixed up with how I've labeled this. Because if you take a look, the chemical shift lines up, right? We are de-shielded, more de-shielded. We are downfield. We are above 2. We have our CH3, no neighbors, okay? On the other side, right, we're going to have a CH3. I won't draw that quite yet. But let's see if we can maybe draw A, make sense of it. I initially thought of something like this. If we had 2 hydrogens here, which we do, we have no neighbors, that explains our singlet. I believe that characterizes A pretty well, okay? And then we have 6 carbons total, 1, 2, 3, 4. I've drawn 4 of them. Let's finish the rest of the structure, 5 and 6, and let's see if that explains, if it lines up with the table. This already looks good to me, right? D is this terminal CH3 that has 2 neighbors. It really all depends if B plays nicely right here, and I think the answer is yes, because we have a quartet. So B, we were looking to have 3 neighbors, and we indeed do with that CH3. We have the chemical shift lines up, it's low 2s, we are alpha to a carbonyl. So this is our structure. You put little check marks over here, smiley face, and I hope that was a sufficient explanation of 2. I just don't want to make this video super long. Okay, so on to problem 3. Okay gang, problem 3. I like this problem because it shows us a good example of how you can have 7 carbons or many carbons in a structure but have very few peaks or signals in your NMR spectrum, okay? Because symmetry. All right, so if we take a look here, remember the process, do not forget the process, always use the process. First and foremost, degrees of unsaturation. We have one of them, we use our handy dandy formula, not notebook, handy dandy formula, 1 degree of unsaturation, so we're dealing with 1 ring or 1 double bond. Have some symmetry here. So if we make our chart, right, we see we have a peak at 3.3. I'm going ahead and, I forgot to label these A, B, and C. So we have a peak at A at 3.3, a peak at B at 2.2, and then a peak around 1, maybe 0.9. They're all singlets, so no neighbors, right? This is goose eggs in the neighbor column. So very easy to fill out. We see we have many hydrogens that correspond to letter C, that signal. That means there's a lot of symmetry there, okay? So I want to actually start there first. So if you can see, the appearance I'm suggesting is that we actually have kind of like a T-butyl group at the end of our chain. And now, it's weird, and you might think, Joe, how did you know that? Well, you get it after you do some problems, but think about this, right? Think about this, because it makes sense. We have 9 hydrogens, right? So think about that, right? There's, this is typically indicative of, this would be a good example of a CH3 that has no neighbors, right? Well, if you have 3 CH3s, right, like a turkey's foot at the end of a chain, that means you are then attached to a quaternary carbon, right? Because if the chain must go on, right, let me just even draw something like this. We're really dealing with these positions right here. These are all equivalent, and think about what they're attached to. That's a carbon with no hydrogens, right? So these carbons have no neighbors, okay? And there's 3 hydrogens each. So that would mean they're all going to have the same peak, 3, 6, 9. You're going to have 1 peak that's going to be very upfield, right? So, and it's going to have an integration number of 9, okay? So that's why I think this is a giant clue for us. So if that's the case, if this is what we look like here, which I believe it is, that means it probably rules out the ring and we have some type of double bond going on. So let's go upfield down this way. So if we look at B, we have a singlet at 2.2. Our chemical shift table tells us that is very indicative of being alpha to a carbonyl. And like we've seen in examples past, that means we probably have, our integration number is 3. So not only are we alpha to a carbonyl, but that means the carbon we're attached to is 3 hydrogens. That means it's a terminal CH3. So we are alpha to a carbonyl, and we are on the end of a chain. So what we've really found is the ends of our chains. So if you want to think about it, we've identified, and I'll draw a little squiggle. So we've already, identified, and I'm going to say, like, I'll cut it off here, 1, 2, 3, 4, 5, 6 carbons already, okay? And so really we have 1 carbon and 1 oxygen left. And if we look at A, we have a 3.3 chemical shift. It's a singlet, so no neighbors. And we're pretty downfield. And if you look at your chemical shift table, if you're in that mid-3s, I know in the previous example we had that, that carbon wedge between the 2 carbonyls. But very indicatively, if you're in the low 3s, mid-3s, you are in ether country, okay? So no neighbors, and an ether. Now think about this. Piecing together what we've known, or what we've figured out. I feel very good about this, right? This to me is saying, this is peak B right here, okay? Obviously no peak for the carbonyl carbon. Now, what I'm gonna do is I'm just gonna connect the chains like this. So, 1, 2, 3, 4, 5, hold on, I'm not doing math well. Let me make sure, okay. 1, 2, 3, 4, 5, 6, 7. Okay, I'm not saying this fits our formula, but I just want to illustrate a point. These carbons right here, CH3, CH3, and CH3, this is peak A, okay? This is peak A, okay? So, right, and that makes sense because we have the quaternary carbon, no neighbors, so that looks good. And definitely corresponds to 9 hydrogens. I think that's good for A. Now, if we left it like this, right, we would be not abiding by our chemical formula because we don't have a second oxygen, okay? So we need that. However, if we look at this right here, right, integration, so this could be potentially peak A, and it does work because we have 2 hydrogens, that's our integration number. We have no neighbors, singlet, except we can't justify this chemical shift. This to me would be something a little bit more in the range of 2.3, 2.2, you know what I mean? However, if we make this ketone, and of course I'm gonna have to ruin my good drawing, if we make this ketone into an ester, where this is A, and this, oh, nope, this is A and this is C, I hope you'll think that this makes more sense because not only do we have, the same, there are no neighbors here, but now we've just added a component that makes this, these 2 hydrogens more downfield. Right now we're in ether country. So I hope you see that 1, 2, 3, 4, 5, 6, 7 carbons, 3, 5, that's 5, plus 9 is 14, 2 oxygens, got the structure. Okay gang, one more, let's finish part 1 strong. Okay gang, problem 4, let go. Alright, if we take a look here, remember the process. Degrees of unsaturation, fill out your chart. So if we take a look here, we actually have 0 degrees of unsaturation. So first of these 4 problems with no degrees of unsaturation. Then we look to our handy dandy spectrum, and then we fill out our chart. So if we take a look here, I think you're seeing, okay, we have 3 signals and we have 8 carbons and a whole bunch of hydrogens. So maybe some symmetry is going on. So if we take a look down here, I think peak signal C is our most interesting. So it's very upfield, right? So there's no, don't even think that there's anything electronegative surrounding it, right? Very similar to where we just have regular old, CH3s and whatnot, and the integration number is divisible by 3. So you think maybe this is corresponding to some factor of terminal CH3 groups. So, and we only have 1 neighbor. So that got me thinking, 1 neighbor, right? And then we have so many of these CH3s. What if we had 2 of them and we had 2 of, more specifically, what I would maybe call an isopropyl group, where you have 2 CH3s with just 1 neighbor right there. Then you have the rest of your chain, right, from the carbon that would only have 1 hydrogen right here. So this would be 6, and then the other side of your chain would be just like that. So really what I'm saying is, what if we had a CH3, you have the 1 hydrogen right there, the chain continues, and then right along here, you have another CH3, another CH3, another H, so that your splitting pattern, right, this would definitely be a doublet, 6 hydrogens here, 6 hydrogens here, 12 overall, and you have doublets on both ends. So I think this is a huge key in this problem to recognize and take advantage of. So, and to further corroborate that, if we take a look at B, all B is a slightly more downfield, okay? And we do see that there is a downfield presence here. We have that in A. So this has a crazy splitting pattern. This is a no net. This has tons of neighbors. It has 8 neighbors. okay? And there's an integration number of 2, so maybe we have 2 of these as well. So what I was thinking is maybe the peak B corresponds to that hydrogen right there. Maybe, you know, the 6 neighbors comes from right there, and then the other 2 get made up on the other side of this carbon, and we haven't drawn that yet. And then we look to peak A. We look at peak A, we see there's an integration number of 4, which would work if we had hydrogens here and here. That would satisfy our splitting pattern for the carbon right here that we're saying is peak B, right? So that all makes sense. It is a doublet. It is going to split with one other hydrogen, so that connecting our chain like this does make sense. However, that doesn't explain how A is so downfield. But we see we have 1 oxygen. We see that the chemical shift for A is in ether land. What if there's an ether just stuck in the middle of this molecule? So I think a molecule that looks like this, and again, let's draw and check ourselves, might just work. So here's our CH3s right here. I'm saying these terminal carbons are corresponding to peak C. C, 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 and C. That explains 12, the integration number of 12, 3, 6, 9, 12. Then we have these hydrogens right here, which I'm saying corresponds to B, our integration of 2. And if I fill these in, we can check the splitting pattern, right? Maybe it is a little slightly downfield because of the oxygen being so close, right? Of course, these hydrogens will be more downfield than this, but we're only 2 carbons away, so it makes sense that maybe it is a little bit more downfield from 1. So I think that is a thumbs up. Last but not least, A, we're in that mid-3 chemical shift range. We are a doublet, that's right. We only have 1 partner, 1 neighbor to split with. And we have a total of 4 hydrogens. This structure, now let me label that. This is A and A. This structure satisfies the information given. Gang, I hope that this gave you some answers, some clarity, maybe unlocked some brain potential. If you're having some trouble with proton NMR, just keep at it. I promise you it will get easier. You'll get better at recognizing things. You'll get better at just the process of digesting the information and figuring out what structures fit the spectrum you are given. If you're watching this video, that means you've donated some money to jOeCHEM. You've supported the website financially, and I can't thank you enough. Thank you. Thank you for using jOeCHEM. Thank you for supporting the cause. I'm so glad and humbled you're using it right now as an organic chemistry tool. I hope you're using it towards the end of your time taking organic chemistry. But no matter what, I hope to see you all in the next video.